In April 2026, 4 astronauts aboard Orion completed the first crewed flight beyond low Earth orbit since Apollo. They traveled to the vicinity of the Moon, observed its far side in detail, and returned safely to Earth. That mission proved the transportation system. It did not prove that we can stay. The lunar surface is covered by a layer of regolith created over billions of years by micrometeorite impacts. There is no atmosphere to weather these particles. They remain sharp, irregular, and electrostatically active. Apollo astronauts discovered this the hard way. Dust abraded seals, stiffened suit joints, scratched visors, and produced respiratory irritation. It infiltrated every system that was not explicitly protected. Today we understand the physics better. Solar ultraviolet radiation and the solar wind charge the particles, causing them to levitate and cling aggressively to any surface. The dust does not care about our timelines. We have circled the Moon. Now the real engineering challenge begins. Constructing infrastructure that can survive an environment that is continuously trying to degrade, abrade, and contaminate it, so that the same systems can one day support human presence on Mars. The Moon is the proving ground. Phase 1 is just the beginning. The decision to establish a sustained presence on the Moon before committing to Mars is not sentimental. It is an engineering necessity driven by physics, logistics, and the need for rapid iteration. A one-way trip to the Moon takes roughly 3 days. Communication latency is measured in seconds. A mission to Mars requires 6 to 9 months of transit each way, with communication delays of up to 22 minutes. Failures on the Moon can be diagnosed and corrected in near real time. Failures on Mars cannot. The chosen location is the lunar South Pole. Ridge lines near Shackleton Crater receive near-continuous sunlight. While adjacent permanently shadowed regions contain water ice, feedstock for oxygen, hydrogen, drinking water, and rocket propellant. After the successful Artemis II flyby, NASA refined the architecture. The Lunar Gateway Station has been paused. Resources are redirected to surface infrastructure. 2 competing commercial human landing systems, SpaceX Starship HLS and Blue Origin Blue Moon, provide redundancy. Artemis III in 2027 will test docking and operations in low Earth orbit. Artemis IV, targeted for early 2028, will attempt the first crewed landing. This approach allows a high cadence of robotic precursor missions under the Commercial Lunar Payload Services Program. More than a dozen deliveries are planned in the near term to characterize sites, demonstrate mobility, and emplace initial infrastructure. Apollo taught us that the surface environment is hostile. Any long-duration architecture must treat dust as a primary design driver. NASA's current plan proceeds in 3 deliberate phases. Phase 1 emphasizes reliable access. Phase 2 begins semi-permanent habitation. Phase 3 targets continuous human presence supported by nuclear power and in situ resource utilization. By solving power, dust, and life support on the Moon, we develop the exact capabilities required for Mars. The Moon is not a distraction from Mars. It is the necessary proving ground where the infrastructure will first be forced to work. That work is already underway. The landers are in production. The engineering constraints are known. The solutions are being built. After Artemis II, NASA reoriented the program towards sustained surface operations. The Lunar Gateway was paused. Resources shifted to a phased moon base architecture centered on the lunar South Pole. Where elevated ridges receive near-continuous sunlight, while permanently shadowed regions hold accessible water ice. 2 commercial human landing systems provide resilience. SpaceX's Starship HLS offers massive cargo capacity, but it requires multiple orbital propellant transfers. Blue Origin's Blue Moon provides a complementary architecture. using liquid hydrogen and oxygen. Artemis 3 in 2027 will test docking and operations between Orion and these landers. Artemis 4, targeted for early 2028, will attempt the first crewed landing since 1972. The first major cargo element, Blue Moon Mark 1 Endurance, is targeted for early 2027 delivery to the Shackleton Connecting Ridge. It carries the SCA-LPSS stereo camera system to quantify plume-regolith interaction at the high thrust levels. Surface mobility begins with lunar terrain vehicles. NASA awarded Astrolab and Lunar Outpost contracts for the first phase. These vehicles must traverse 20-degree slopes, survive 150 hours in shadow, and operate at 10 kilometers per hour. NASA's phased approach begins with high-tempo robotic delivery. Phase 1 and 2 survey sites and in-place initial power assets. Phase 3 delivers larger habitats and the first operational fission surface power systems capable of continuous output. Lunar dust is not ordinary dirt. The particles are razor-sharp glass and mineral fragments, many under 20 micrometers. In the vacuum, they charge electrostatically. Apollo astronauts reported stiff suit joints, scratched visors, and contaminated seals. The primary active solution is the electrodynamic dust shield. Transparent electrodes generate traveling electric fields that transport particles. Complementary passive coatings and suit ports form the operational barrier. Without these defenses, mechanisms seize and radiators overheat. The decisive step is fission surface power, Lunar Reactor 1, targeting 20 to 40 kilowatts continuous electric output. Radiation protection relies on local materials. 1 to 2 meters of regolith overburden reduce cosmic ray doses to acceptable limits. Every element is designed to function in the continuous dust environment. The architecture prioritizes modularity and the ability to expand. Sustainable presence requires in situ resource utilization. The most abundant resource is the regolith itself, which contains 40 to 50% oxygen by weight. Locked in silicate and oxide minerals, one leading pathway is molten regolith electrolysis. Regolith is heated above its melting point, typically 1300 to 1600 degrees Celsius. An electric current passes between electrodes. Oxygen evolves at the anode, while metallic alloys collect at the cathode. No chemical reductant is imported. Energy cost is 20 to 60 kilowatt hours per kilogram of oxygen. Electrode durability remains a challenge. Carbothermal reduction offers an alternative. Carbon or methane reacts with regolith oxides at high temperature to produce carbon monoxide or dioxide. Blue Origin's Blue Alchemist system integrates molten regolith electrolysis with downstream processing to produce oxygen, silicon for solar cells, and aluminum wiring, demonstrating an end-to-end path from soil to power system components. Polar water ice provides a second, often preferred feedstock. Ice can be extracted by heating, then electrolyzed into hydrogen and oxygen. The hydrogen can support life support and propulsion. Permanently shadowed regions near the South Pole are the primary targets. Accessibility and concentration are still being quantified by robotic missions. Beyond volatiles, regolith can be sintered or 3D printed into landing pads, roads, radiation berms, and habitat shielding. Microwave or laser sintering is used. Early demonstrations focus on dust-free landing zones that also mitigate plume ejecta hazards for subsequent vehicles. Pilot-scale plants aim for 1 to 10 tons. Scaling to the hundreds of tons required for propellant production demands multi-megawatt continuous power and robust, dust-tolerant mechanisms. The first systems will be power-limited and experimentally intensive. Later systems must become industrial. ISRU closes the logistics loop. Every kilogram of oxygen or structural material produced on the Moon is a kilogram that does not need to be launched from Earth. The same principle, applied to carbon dioxide and water ice on Mars, becomes the foundation for return propellant. The systems are proven here first. The technical barriers are clear: energy intensity and durability. Progress is measured in hours of operation and oxygen yield. Those metrics are advancing. The moon is not the destination. It is the proving ground. Every critical system required for sustained presence on Mars must first function on the moon. Continuous power through extended darkness. Closed-loop life support that recovers more than 98% of water. Radiation protection against cosmic rays, and in-situ resource utilization that turns local materials into oxygen and construction feedstock. The advantages of sequential development are decisive. Round-trip light time to the moon is 2.6 seconds. To Mars, it ranges from 8 to 40 minutes. Flight opportunities to the moon occur frequently. Earth-Mars transfer windows open only every 26 months. A failed power system on the lunar surface can be iterated within months. On Mars, the same failure costs years. Nuclear fission surface power systems under development for the lunar night are directly extensible to Mars, where dust storms obscure the sun. Regolith-based radiation shielding techniques and electrodynamic dust shields all transfer. Starship and Blue Moon landers become the templates. Life support is the most unforgiving common requirement. On the moon, resupply remains feasible. On Mars, it does not. Systems that achieve high recovery and reliable thermal control under partial gravity must be proven where failure is recoverable. By establishing high-cadence lunar operations, we develop the operational muscle memory that a multi-year Mars campaign will demand. The moon is where we learn to live off-world. Mars is where we must already know how. The engineering problems are related, but the stakes are not equal. Solve them first where the feedback loop is short. Then apply the solutions where the distances are measured in hundreds of millions of kilometers. That transition begins with the vehicle that will attempt both. Part 6: Mars Colonization. The transportation foundation for Mars is Starship, a single vehicle capable of delivering over 100 tons of payload. Achieving that capability requires solving a problem never demonstrated at scale: cryogenic propellant transfer in orbit. Current vehicle designs carry approximately 1,500 tons of liquid oxygen and liquid methane at full load. After reaching orbit, the ship is dry. Multiple tanker flights must transfer propellant before a departure burn. Estimates range from 8 to more than 15 flights depending on efficiency. Demonstrations of this transfer remain on the critical path. Uncrewed cargo flights are targeted no earlier than 2028. Tesla Optimus robots are planned as the first surface agents, surveying resources and performing construction tasks before crews arrive. Entry, descent, and landing of a 100-ton class vehicle is a distinct engineering problem. Mars's atmosphere provides insufficient drag. Solutions center on large heat shields and supersonic retropropulsion, firing engines against the direction of travel while faster than sound. Once on the surface, return propellant must be manufactured locally. The primary pathway is the Sabatier reaction, combining atmospheric CO2 with hydrogen. The water is electrolyzed to recover oxygen for the oxidizer and to recycle hydrogen. The result is liquid methane and oxygen produced from Martian air and ice. Producing the hundreds of tons of propellant demands continuous multi-megawatt power over many months. Solar arrays suffer during global dust storms. The architecture relies on a hybrid approach: solar for reliability and fission surface power for baseload and storm survival, estimating 1 to 10 megawatts. Measurements show an average cosmic ray dose equivalent of approximately 0.6 millisieverts per day. Multi-year stays require substantial shielding. Life support must be nearly closed. Water recovery rates above 98%, CO2 reduction and oxygen generation are mandatory. resupply is years away. The gap between ambition and capability is significant. Key systems are not yet proven. Lunar progress de-risks many elements, but Mars still requires its own uncrewed precursors. Next, timelines and risks. Current planning places continuous human presence on the Moon in the early 2030s. Human landings on Mars remain realistically placed in the mid to late 2030s. Physics-constrained schedules account for orbital refueling, EDL, and power. The principal risks are technical and operational. Dust abrasion and contamination over multi-year timescales must be quantified. Continuous multi-megawatt power must be demonstrated and maintained. Propellant production rates must scale from pilot levels to the hundreds of tons required for vehicle return. Each of these systems has clear development paths. Closed-loop life support must achieve and sustain recovery rates above 98% under partial gravity. None is yet proven at the required scale and duration. The ecosystem is broader than any single agency. Commercial providers supply landers, mobility systems, and increasingly the power and ISRU elements. International partners contribute modules, science, and logistics. The common requirement is that the underlying infrastructure must function reliably before expansion. Success is defined not by the first landing, but by the ability to stay, expand, and eventually return without continuous logistical dependence on Earth. The engineering now underway on the Moon is the necessary first step toward that capability on Mars. We began with the dust, the silent, continuous adversary that abrades, contaminates, and degrades every unprotected surface. That same environment will confront every habitat, solar array, and mechanism we place on the Moon. The response is not rhetoric, it is engineering. Dual commercial landers reduce schedule risk. Electrodynamic dust shields and advanced coatings attack the problem at its root. Fission surface power addresses the long night. Molten regolith electrolysis begins the process of turning the soil itself into oxygen and structural material. Closed-loop life support and radiation shielding techniques are being refined where the communication delay is measured in seconds rather than minutes. These systems, proven and iterated on the Moon, become the foundation for Mars. The distances are greater, the launch windows rarer, the consequences more absolute. But the physics problems, power, dust, radiation, resource extraction, life support, are variations of the same challenges. The physics is unforgiving. The engineering is underway. What we build on the Moon will determine whether Mars remains a distant target or becomes the second home of a multiplanetary species. Foundations beyond Earth. A future in the stars is within our reach.